Hello, this is Jennifer Martinez, and in this video we're going to discuss the definition of continuity. And we're going to start with a graphical viewpoint, continuity on an interval. A continuous function has a graph which can be drawn without lifting the pencil from the paper. For example, let's look at this function. This function is a polynomial, and it turns out that all polynomials are continuous on any interval. The graph of this particular polynomial is right here down in this figure. Here it is. And you can see if I go from left to right and I draw this graph, or if I'm about to draw this graph, I never have to lift my pencil. So it is continuous. And again, that happens with all polynomials. Looking at our next example is an example of a rational function. And a rational function we know is not defined at 0. So it's not going to be continuous there. And if you can see, if I try drawing my graph from left to right here, when I get to 0 here, I have to lift up my pencil to get over here. So it's not continuous at 0. It's not continuous on any interval containing 0 because f of 0 is not defined. In the last example here, the p of x is a step function. And you can see that it's not going to be continuous because I cannot lift up my pencil. But it turns out that f of 1 is defined, but it's still not continuous. So how are we going to handle that? By the way, this example said a company rents a car for $7 per hour or a fraction thereof. So it costs $7 for the trip of 1 hour or less. So right here it's a constant line from 0 to 1. It costs $7. $14 for the trip between 1 and 2. So again, it's a horizontal line, right, between 1 and 2, not particularly at 1, but at 2. And then so on. If p of x is the price of the trip lasting x hours, so that's what we're graphing there, then its graph is a series of steps. This function is not continuous on any open interval because it jumps at these points. Which is going to bring us to our next definition, or a formal definition of a continuous function. A continuous function, or a function f, is continuous at x equals c at a particular point if f is defined at x equals c, so that was what was wrong with our middle graph there, middle example, and if the limit as x goes to c of f of x equals f of c. So here, we notice that the limit, let's just talk about 1 for a moment, at x equals 1, let's just check out that hole, of p of x does not exist. And that makes sense because we notice that on the right side, if we go to take the limit as x goes to 1 from the right side, it is 14 coming from the right side. Coming from the left side, as x approaches 1, it approaches 7. And those two numbers are not the same. That is going to be actually discussed more in the next section when we talk about left and right side limits. Because the left and right side limit is going to exist, but the actual full limit does not exist. So obviously, it doesn't equal p. P of 1, by the way, is defined. Unlike the middle example, it is 7. But obviously, it does not equal that 7 because it doesn't exist. It has to exist. It has to be defined from here, and it has to equal each other. We're at the polynomial here. It did do that. So let's look at another example. let's look at this piecewise. This is called a piecewise function. Let's discuss the continuity of function g. So function g is sine of theta over theta, which is this graph right here, is not defined. G of 0, well, it's this, but this function right here, sine of theta over theta, is not defined at 0. So it actually, if you graph this on the graph calculator, it's fine at every point, but 0, because 0 is undefined. So instead of being an asymptote, like the rational function that we saw above, it's now just a hole. Still not continuous, because when I try to draw my pencil here, I'm going to skip. So it's more like our step function, isn't it? But look at the limit exists. So if I look at the limit as theta goes to 0, because I know that 0 is my problem point if it's not continuous, of g of theta, it is 1. Because when I go to from the left, no matter which way I come at this, the y value is always 1. G of 1/2, on the other hand, G of 0, on the other hand, is 1/2. Went backwards there, right? G of 0 we know is 1/2. And again, it's not continuous, because this limit is 1, and the value, plug in the value there, is 1/2. G of theta is not continuous at x equals 0, since the limit as theta goes to 0 of the function is not equal to g of 0. This side is 1, this side is 1/2. It does not work. What can I do to make this function continuous? Instead of 1/2 here, if I put a 1, plugged up that hole, it would have been continuous. So let's look at this piecewise function. I did just that. This one's going to work, because if I look at the graph, this is the same graph as that with the hole, and then I'm going to, at x equals 0, I'm going to plug up that one. And you can see here that the definition does work, because the limit as x goes to 0 of the function, let's make this f of x, we know is going to be 1, because we're going to look at values that are not exactly 0, and we're going close to 0. That's 1. And f of 0 is also 1. So therefore, the limit as x goes to 0 of f of x equals 1. So it's continuous, because it's also equal to f of 0. And our definition is satisfied. So therefore, f of x is continuous at x equals 1, and then I just rewrote that. Actually, it's continuous for all values of x on interval, because obviously that's the only problem point. All the other points, the limit will definitely equal the value of the function. So it turns out that it's continuous everywhere. So let's look at the absolute value of x. Is that continuous? If you remember, the absolute value of x is defined as a piecewise function. It's x if x is bigger or equal to 0, and negative x if x is less than 0. Whoops. If you graph the absolute value on your calculator, it will look like a V, because it's the line y equals x. This is what h of x is. when x is bigger or equal to 0. It's actually 0 when it's 0. And then it's negative x when x is less than 0. You can see it's a v. It's definitely continuous at 0. I don't have to jump anywhere. And if I look at the limit as x goes to 0 of f of x, it's 0 on both sides, which is the same as f of 0. All is good. So the answer is yes. It is continuous. What about if I innocently divide an x, the absolute value of x over x? What does that look like? Well, we know that from above that the absolute value is x, but I'll just add this other x. If x is bigger or equal to 0, and it's negative x, but we have that other x, if x is less than 0. And actually, I made a mistake here. This should just be plain greater than now, isn't it? Because at x equals 0, it is undefined, right? G of 0 is undefined. So we do have to not put that a less than or greater than or equal to there. I can simplify this to be 1 for x is bigger than 0 and negative 1 when it is less than 0. So if I was to graph that, it's the horizontal line. We'll call this 1 right here. When x is bigger than 0, that's supposed to be a line. And then it's a horizontal line, right? When x is negative, it's always going to be, the y value is always going to be negative 1. Again, if you graph that on your calculator, that's what you would get. And we can see here that not only g of 0 is not defined, so we can't even add any value to plug it up. It's not going to be continuous because the limit as x goes to 0 of g of x is that usually say does not exist, but does not exist or not defined as well, right? Because again, as x goes to 0 from the right, these values, it has to go the same value no matter which way I come. And this way it's going to 1, and on the left it's going to negative 1. And that does it. The answer is no. It's not continuous. I hope that helps.